All right, so now let's learn our first new type of reaction for this chapter. This is a Simmons-Smith reaction. It's actually pretty easy. And this is going to use yet another metal, zinc, act with a alkyl halide very similar to a Grignard, where it just sort of inserts itself between that carbon halogen bond. Okay, and you're also going to do this in the presence of an ether or a an aprotic solvent. And note that the carbon zinc bond is not quite as polar as the carbon magnesium bond, so we don't expect this to be quite as reactive. It's not going to have the same sort of reactivity as a Grignard. It's actually going to have one very specific type of reaction that we're going to learn about, which is called a cyclopropanation reaction. Okay, so let's just pick this word apart real quick before we even look at what happens. Cyclo, so we're going to be forming a ring. Propanation, so we're going to be forming a three-membered ring here. Okay, and this is the combination of reagents that we're going to specifically use for this Simmons-Smith type reaction. You have this diiodomethane reacting with this zinc copper mixed in an ether, and that creates this iodomethyl zinc iodide, not ion, but compound. Yeah. Anyways, this is going to be the active player in this particular reaction here. And what happens is really the key chunk of this compound here is this right here. This is what's going to be inserted into, it's going to react with an alkene. So imagine you have a double bond, you're going to insert this chunk right here, and that's what's going to create your new three-membered ring. Okay, this is sort of a little electron pushing-esque thing going on here. Again, we're not going to worry about mechanisms in this particular chapter, but that's exactly what happens. Again, remember I was saying this is the key chunk, this carbon that's bound to two hydrogens, and that's exactly what's going to happen. You're going to have that be attacked by a double bond, and that carbon's going to sort of insert itself, creating a cyclopropane ring. All right, so this is the cyclopropanation product that we get in these Simmons-Smith reactions. Okay, these reactions are also stereospecific. So if we start out with the trans alkene, now we have, these are our Simmons-Smith combination of reagents here. We're going to wind up with a trans cyclopropane compound. And if it's trans, remember that it's also going to have an enantiomer associated with it as well, right? So if I'm asking you to draw all stereoisomers, make sure that you give me that one as well. In this case, it would just be with the dashes and wedges reversed. Okay. If you have a cis alkene, you're going to get a cis cyclopropane ring. Those actually don't have enantiomers associated with them. They are identical to their mirror image, so that's nice. Okay. So now let's just do some more example. Again, this is a pretty simple reaction, but predicting products is obviously a big part here. So again, we have our alkene. What we're going to end up forming is a triangle where that alkene used to be. So that's exactly the product that we would expect. Likewise, if we're starting out with a cycloalkane, we would expect to get that product here. This is, you could see the wedges. This is going to give you a cis product. It has to be cis because the ring's locked, right? So this is you're starting out with cis over here. We don't even really bother to call it cis because it's locked in a ring, but it is. And so we're going to get a cis product. And then if we want to do the retrosynthesis, what alkene would we need to start with to get to this product here? Remember that this tip of the triangle is going to be that newly inserted carbon. So we're going to get rid of that. And there should be a double bond between those two carbons in our starting reactant. So in terms of the retrosynthesis on that, this would be our starting material. Similar type of reaction, another cyclopropanation reaction. It actually doesn't even involve a metal, so I'm not entirely sure why it's in this chapter, other than that it's very similar to the reaction we just learned about. But that is starting out with like trichloromethane in the presence of a base will produce what's called a carbene, sort of a carbanion, but super tiny. And this will also react with a double bond in a cyclopropanation reaction, right? So both of these are cyclopropanation reactions. The only difference being is that instead of having 2 hydrogens on the carbon, now you have 2 chlorines. The base of choice is tert butoxide. Really, any strong base would work as long as you're going to start out with your trichloromethane. And again, just like the other reaction, the Simmons-Smith reaction, this one will preserve the stereochemistry. So if you started out with a trans, you'll get a trans product as well. Plus it's an enantiomer. Okay, so just to review, this is a sort of quick summary of our cyclopropanation reactions. You have the Simmons-Smith reaction, which is the organometallic one. Zinc is the key player here. And you're going to start out with diiodomethane. You can do the same sort of thing. Oh, and that inserts this CH2, creating a cyclopropane. You can do something very similar, starting out with trichloromethane in the presence of a strong base, and then you'll also get a cyclopropane, but now you have 2 chlorines bound to that carbon.